So let us continue with our discussion, and we discussed microservices. And in the microservices, one important aspect that I had brought is people basically go for eventual consistency. People really don't look at traditional database level consistent approach. So the example that I showed there is in a banking scenario, there are accounts being maintained, and then there is a money transfer service. So the simple debit and credit on two accounts, which traditionally can be solved by defining a database transaction, need to be addressed in a different manner. And I said that instead of such a transaction, we are going to basically have a message based interaction where there will be messages that will indicate that debit is being initiated, credit is being initiated, and so on. And the services are going to subscribe to different messages. So it's purely asynchronous message driven communication. And then at any given point in time, or rather when the transaction is over, when the transaction is over, it is not necessary that the database consisting of accounts will be in a consistent state. So, but however, after some time, when these messages are analyzed and essentially those actions are actually introduced and actions are reflected on the database, then this database becomes consistent. So database does not become consistent immediately, but it becomes consistent after some time. So this fact that database is not consistent immediately but becomes consistent after some time is called eventually consistent system. Now, as an architect, when you are designing systems for cloud and you are taking microservices based approach where you are subscribing to different types of events from other service providers, this is a very important part. This eventually consistent system is a very important part that as an architect you need to understand and you need to implement. Behind eventual consistency, there is a very well-known theorem called CAP theorem, which is what I'm going to talk now. So CAP theorem is basically was first proposed sometime in early 2000, actually maybe late 90s, and it says that no distributed system can achieve all of the three properties, and these are consistency, availability, and partition tolerance. Consistency means that data will be consistent throughout the distributed system. Availability means that data and also a service will always be available. Partition tolerance means that the system will not fail even when the network is disconnected. So the CAP theorem says that in a distributed systems you cannot achieve all. You cannot have a consistent system as well as it is available, as well as it is partition tolerance. You need to sacrifice one of them. So let's understand this CAP theorem and what it implies. So imagine that there is a distributed system which keeps track of a single piece of data. Now this data is actually copied in multiple nodes A, B, and C. So what that means is that if the data is changed, then the change should be reflected onto A, B, as well as C. Now assume that all of them are consistent. Now suddenly the misfortune strikes and the system is now partitioned into A, B, and C, meaning that the connectivity with C is lost. Therefore, so in that case, what is going to happen? Now a client accesses C and then makes a change to the data in C. Now what should we do in that case? One could be that I can accept the write, and I know very well that neither A nor B will know that this new data has come, the data is changed until the partition is recovered. Till that time A, B and C will not be consistent, but I still allow the write. Second could be that I refuse the write, knowing that the client might not be able to contact A and B until the partition held. So I say that I cannot accept the write request. So I have got only two choices. So first one is choosing consistency over availability, where I refuse to write. In that case, when I choose consistency over availability, it has to guarantee that atomic reads and writes are always consistent by refusing to respond to some requests. In this example, option 2, I would rather refuse a request than to be inconsistent. In that case, I say that I am choosing consistency over availability. So the design option could be that you could decide to completely shut down the entire system, or refuse writes like a two-phase commit, either everything passes or everything fails. Or you could respond to reads and writes for pieces of data whose master node is inside the partition component. So that's a slightly modified version, that if you know that the master is already inside the partition component, in that case you could accept it. In this case, suppose A is a master, and if the write request comes to B, in that case B can accept the request knowing that A and B are connected. The second option is choosing availability over consistency. In that case, I'm going to choose option 1, where I'm going to respond to all the requests, potentially even returning the stale reads and accepting conflicting writes. In this case, I accept the write, C is modified, A, B are not. So if there is a query that lands up onto A, then they're going to get a stale data. And in fact, A, B and C are not even consistent. Now, sometimes, so how would people know that, how would the system know that A, B and C are essentially are not consistent? So these consistencies are typically resolved via causal ordering mechanisms like vector clocks. These vector clocks are associated with the data, using which one can know that the timestamp of C is actually more than timestamp of A and B. As a result, the value that is there in C should be actually copied to A and B. So this is how the consistencies are often resolved. Sometimes application specific conflict resolution procedures are also adopted. For example, Dynamo actually offers both this application specific conflict resolution as well as vector clock based. Cassandra's hard-coded logic of last writer wins logic basically is used for conflict resolution. So either one can choose Cassandra type approach, where last writer wins is approach is chosen, or Dynamo typically can use this complete timestamp based approach. So as a software architect, how do you trade off between C, A and P, consistency, availability and partition tolerance? Consistency is basically replaced with eventual consistency, but availability is not really compromised. That's a very important thing when you are architecting for cloud, because in the cloud, when you are building software as a service, then you cannot afford to have the service down. Therefore, the service must always be available, even if it is inconsistent for a certain time. Now, obviously, nobody would like the system to be inconsistent for a long time. Therefore, there must be some time bound within which the inconsistency should be resolved. Now, typically nodes across partitions are allowed to be inconsistent for some time, and then it becomes consistent. Now, as an architect, when you are choosing for eventual consistency and you are, let's say, building an application, for a client, or you're building a product, or you're building a software as a service. In that case, there can be some SLA or service level agreement that might say that no more some X% data should be stale, or there could be another SLA that might say that it shouldn't take more than T seconds to be consistent. So these are the SLAs typically the end customers, consumers, clients, they might just put. As an architect, your design challenge is that how do you ensure that this SLA is met. Now, availability and partition tolerance, which is latency, is typically preferred over consistency. There are many examples. For instance, Facebook. In Facebook, user should always be able to respond, but they are okay with a delayed news feed. So delayed news feed is basically an example of temporary inconsistency, whereas Facebook user should always be able to respond. That's about availability. So here availability is chosen over temporary inconsistency. Amazon shopping cart also follows the same logic. It really does not require the traditional database ACID property. Twitter, for example, same thing, the timeline may be delayed, but it must be available. Fund transfer between banks, the example that I showed earlier, it allows a delay of 24 hours, and within that 24 hours there could be a inconsistency that your account may be debited but the target account may not be credited. So there is a delay of 24 hours. So that's the delay that that could be there upfront, given by the bank, that it shouldn't take more than a day to be consistent in this case. So this is also an example of eventual consistency. So I actually showed these 4 examples because I wanted to highlight that eventually consistent systems are very much in use all the time. It is not that this is something impractical or this is something too restrictive. In fact, on the contrary, you'll be surprised that end consumers are okay as long as the inconsistency is not for too long. As long as the inconsistency is resolved within certain time, they're perfectly okay with temporary inconsistent data, but they are not okay with unavailability, which is why most of the designs which are software service based consider A and P over consistency. What would be the architect's role? Architect's role would be to implement eventual consistency. There are different design techniques like use of caching, use of replication, message retry, timeout mechanisms. These are all techniques that come handy when you want to implement eventual consistency. You need to also understand various quality attribute trade-offs. For example, the NoSQL database must do a trade-off between availability, latency, consistency, and partitioning. So when you are choosing a NoSQL database, you need to be upfront while signing off with the client about the non-functional requirement or SLAs. That time it needs to be very, very clear. You can't just sign off with a customer where the customer is demanding all consistency, availability, and partition tolerance. In that case, you need to upfront say that that's not possible. So for that, it is necessary to know that what are possible, what are not possible, typically when you are building a distributed system. In addition to this, interoperability, security are also equally important when you as an architect are building software for next generation systems, which is the cloud. So with this, we conclude the CAP theorem, and in fact we conclude this course. So we have covered, in this last lecture series, we have basically introduced cloud computing. We have introduced the basic concepts behind cloud computing, virtualization. Then we talked about infrastructure as a service, a bit of data center, and then as a software architect, what are the important issues that you need to understand and address while building software as a service. Thank you for listening. Goodbye.